for a while, but we're going to be talking about equilibrium. There's translational equilibrium, and then there's rotational equilibrium. And when you put those two conditions together, you get what we call static equilibrium. Translational equilibrium, the following condition must be true. Don't write this down. In English, Josh, we write this. The sum of the forces must equal zero. Thank you. For translational equilibrium, the sum, don't write this down because we can write it shorter. But if you know that all of the forces balance out, if the forces on you are zero, you're in translational equilibrium. By the way, that also means what's your acceleration exactly as a number. Yeah. So if an object has an A of zero, it's in translational equilibrium. We have a fancy schmancy abbreviation for the sum that you've learned in math. Yes? We say this: the sum of all the forces equal zero. Another way of writing this, which we're going to use quite often because we're going to be dealing with angles. Did I say angles? Another way of writing this is to say the sum of all the vertical forces has to equal zero, and the sum of all the horizontal forces has to equal zero. I gotta be honest, I tend not to use those two. This is one time I break it down even further. If the vertical forces are zero, what we're really saying is this: all of the forces up have to equal all of the forces, yes. And if the horizontal forces are balanced, Lean, what we're saying is all of the forces to the left have to equal all of the forces to the, yep. What would be a good abbrev to use for the word up? Or a U? What would be a good, I'll probably use U, D, L, and R in my abbreviating if you look at my answer keys, okay? But yeah, you can also use arrows. I never even thought of that. So here's a nice example. It says, find the tension in each rope if M1 equals 12.6 kilograms and theta equals 34 degrees. You're at a bit of a disadvantage here because you haven't done as much geometry as the students had done 10 years ago or 15 years ago. 15 years ago, Math 12, Pre-Calculus 12 was called Principles of Math 12. 40% of the course was geometry, almost half of it. It was a big chunk. So you're not as adept at moving angles around, but don't worry, I'll show you how to do this. This is a job for a free body diagram. Oh, well, did they give me a picture? What are the, okay, I'll label the picture. Brendan, what are the forces acting on this? Get the obvious one. And I'm going to be fussy. I'm not going to draw the forces on the mass. I'm actually going to draw the forces right where they all connect, right there. So I'm going to have mg down. And then I have two ropes. I'll call this one tension 1. I'll call this one tension 2. Spoiler alert, newer, if the angle is the same, then the tension's going to be the same, but we haven't proved that yet. But just if you're wondering, won't they be the same? They will be. You can do this with components. This is one time I'm going to suggest we use a vector triangle and trig. So we're going to draw a vector triangle. How many forces are there on my diagram? 3. So it's going to be a triangle, but it's going to be a weird triangle because is this sine accelerating? Be stupid obvious. So what's the sum of all the forces going to equal as a number exactly? So my triangle is not going to be adding tip to tail. It's going to be 3 vectors, and 0 is when you come back to where you started from. It's going to be a triangle that completely closes itself. Now, there are 3 vectors, 1, 2, 3. When I draw these, I always draw the easiest vector first. What's the easiest vector to draw? Be stupid obvious here. I'm going to draw mg first. Okay. Then I always draw the toughest vector next. Here, both vectors are of equal toughness, so it doesn't matter. I'm just looking at, I want to have room over here to write. I'm going to do, here's tension 1, here's tension 2, and here's mg. I want to see if I can fill in some angles. Look at tension 2. I notice that tension 2, where it touches a horizontal line, how big is this angle according to the question? If I draw in a horizontal line right there for tension 2, how big must this angle right here be? 34 degrees. Is that in my triangle? Okay. How big is that angle then? What do those two angles add to? 90. See it? So on your calculator or in your head, 90 minus 34, that's going to give us one of our angles. 56? If this was a right-angled triangle, I'm good, and I just need one angle and one side, and I can find the rest. This is not a right-angled triangle, so I'm going to do the same trick I did over here. I notice tension 1 next to a horizontal line is 34 degrees. You know what? I kind of have to go like this. 34 degrees. How big is this bottom right angle? Can you see I've cleverly inserted a right angle triangle, so this one here also happens to be 56. And now I can also get this angle right here. How big is that angle? What does every triangle add to? So 180 minus 56 is what? This is, and I'm going to go darker so I can see 68 degrees. There. I've got all three angles. So one of the skills is, Lean, when in doubt, you add horizontal and vertical lines, and you can hopscotch your way there. You're having to do this the long way. 15 years ago, kids would have glanced at the original diagram and they would have said, oh yeah, that's done, without having to add the horizontal and vertical lines. But okay, we can get there. As long as you know that this is a 90 and that triangles add to 180, we're good. Is there a right angle in this question? Be stupid obvious. I can't use SOHCAHTOA, but we are going to use the sine law, which you're doing some trig right now in pre-calc, or you might remember. What's the sine law? If I generalize it, it says the sine of this over this equals the sine of this over this. Sorry, the sine of this over this equals the sine of this over this equals the sine of this over this. The sine of any angle divided by the side across from it. Which side do I know? mg, because they gave me the mass. So what do you want to find first? Tension 1 or tension 2? I don't care, pick. So I'm going to use, you want me to find tension 1? It's going to be the sine of what goes with mg, 68 over mg, equals the sine of, you said tension 1. What angle goes with tension 1? This 56. Now, I realize they're both 56, but when they're not, this is how we would figure it out. Sine of 56 over tension 1. What's kind of nice is we end up with a cross-multiply equation, which is actually pretty straightforward. Where is the tension 1 right now? On the bottom. Well, you could either do stuff moves diagonally or cross-multiply, but I think if I get the tension 1 by itself, it moves to here. It's going to be mg sine 56 divided by sine 68, which is what? I did like it. I used to do this as the third unit. This is what I did right after forces. And it was nice because it reviewed the sine law and the cosine law, which often you were hitting in pre-calc 12 in the old course right around then. So it was kind of like, hey, let's make this work. What was m? 12.6. G, 9.8 times sine 56 divided by sine 68, and I get that tension 1 is equal to 110.4 newtons. What about tension 2? Well, I'm still going to use what they gave me, which is, I know that the sine of 68 over mg, I know mg, so I'll keep using that pair. That would be tension 2. Noor, which angle goes with tension 2? You know what? It's also sine 56. Do you notice these two equations are the same? I told you if your angles are the same, the tensions will be the same. I'm not even going to bother solving it. I'm going to say, you know what? That's also 110.4. So we say this object is in static equilibrium. Why? Sorry, we say this object is in translational equilibrium. Why? A is 0. The sum of all the forces is 0. You'll notice I really didn't break it down into components. I could have. So the other way to do this, if you don't want to use the sine law and the cosine law, would have been to break this up into components where you have an fx1 and an fx2, and you have an fy2, and you have an fy1, and mg, and fy1 and fy2 have to cancel out mg, and fx1 has to equal fx2, and you can solve it with a system of equations, but it's a lot of writing. It's completely doable with Math 10 systems of equations and Math 10 SOHCAHTOA trig, but I prefer to use the sine law and the cosine law. I think it's a much cleaner way to solve it. Gets you there in way less work. Example 2, are my angles the same this time? The tensions won't be the same. So here they moved the sign over a little bit. It says find the tension in each rope if M1 equals 12.6 kilograms. I use the same mass. Theta is 44 and alpha is 16 degrees. Okay. This is a job for a free body diagram, but Trevor, did they give me a picture? Okay, then let's label the picture, and we're going to label the forces actually where the ropes connect. What are the forces acting on it? Get the obvious one. What else? I'll call this, and you can call this either tension L for left or tension 1 for the first rope, and I'll call this, you can call this tension R for right or tension 2 for the second rope, but there are my forces. I'm going to draw a vector triangle. I'm going to draw the easiest vector first. Niels, which of those three is the easiest vector to draw? I agree. It's going to look like this. And I'm going to draw a fairly big triangle to give myself some breathing room. Then I want to draw the yuckiest one next. They're both kind of yucky, so it doesn't matter. I'm going to go tension 1. And I'm going to go tension 2. Now, this might be terrible scale. This angle that looks like it's nearly 90 degrees might end up being 20. I haven't worried about scale. I'm just trying to get everything in the right place. But now I'm going to do the same trick as I did before. Tension 2, apparently when it hits a horizontal line, how big is this angle? 16 degrees. How big is this angle right here then? Okay, you ready? Tension 2, when it hits a horizontal line, alpha is 16 degrees. Is this tension 2 hitting a horizontal line? How big is this angle as well? How big is this angle? Because that's the one that I want. 90 minus 16. 74? Going to do the same trick with tension 1, but it's a bit more convoluted. Tension 1, when it hits a horizontal line, is 44 degrees. So if I go like this, this angle right here is 44 degrees. How big is this angle in the bottom then? (90 minus 44), 46, 46, I think. Yes. By the way, make sure you either carry the one, or honestly, I've made that mistake so often when it's angles, I always use my calculator because I've forgotten to carry the one more times than I can remember. So this is 46 degrees. How big is this angle then? Well, triangles have to add to 180, so it's going to be 180 minus 74 minus 46. 60? Is that right? Yeah? Okay. And like I said, this is terrible scale. That looks really close to 90 degrees, not 60 degrees, but I've got everything in the right place. Which thing do I know? I know M1G. This is the pair that I'm going to use to find the other two tensions. So I'm even going to draw a little line down the middle of the page like this. My equation is going to be sine 60D over M1G equals, okay, which angle is going to go with tension 1? Yeah, the one across from it. They always go together across from it. Sine 74. So cross multiply, or stuff moves diagonally, or whichever trick you want to use. But I'm going to get tension 1 equals mg sine 74 divided by sine 60. How big is tension 1? Oh, you know what? I can backspace and edit and just change a few things. It is going to be 12.6 times 9.8 sine, 74 over sine, 60. 137 newtons? Or am I wrong? Yep. What about the other one? I'm still going to use sine 60 over mg. I want T2. Trevor, which angle goes with tension 2? So here's tension 2. Which angle goes with it? Yeah, always the angle across from it. 46. That's what the sine law says. So you know what? It's going to be tension 2 equals m1g sine. Oh, I forgot to write the sine on top. I just wrote the angle 46. That's dumb. Sine 46 over sine 60. Mr. Dueck, can I just backspace and edit and change the 74 to a 46? Why, yes, you can on your calculator. If you have a good calculator, you'll find it's the exact same expression, except instead of a 74, I got a 46 right there. Bonus. And I get 102.6. Is that all right? Example 3 says, find the force that Tower B exerts on the bridge. Is this bridge accelerating? I hope not. That's a bad thing. Here, I'm not going to be using a vector triangle. I don't have things coming in at angles. Instead, here, I think I can say, since it's not accelerating, all the forces down have to equal all the forces. Yeah, I think that's what I can say in this situation. F down, the sum of F down equals the sum of F up. Okay, what's F down? 5,800 and 760. What's F up? 1,900 plus FB. Oh, hey, it's nice to be ending the year with equations like this. Not much to it. This, I would even say, a Math 8 kid could probably handle okay. What do you get? Sorry? Oh, I thought I heard an answer. 5,800 plus 760 minus 1,900. 4660? And that's newtons. By the way, as this bus moves to the left, what will happen to FB? Bigger, smaller, or stay the same? What about Fa. How do we calculate that? That involves torques, and that's going to be next lesson. Ooh, Noah, what are they asking me to find here? I think this is a job for a free body diagram. On the 12.3, okay, Noah, what are the forces acting on the 12.3? Get the obvious one. Is there more than one mass in this question? I'll call this one M1G. And normal force number 1, which I think is the same size as M1G because we're not on a ramp. Which way is this trying to accelerate? To the left. That must mean there's a force to the left. Oh, rope. Noah, you agree with me? Tension. What force is pointing to the right, preventing it from accelerating? Yes. In fact, if we're in equilibrium, do you know how big friction is compared to this tension? If it was smaller, how would this be accelerating? If it was bigger, but we're in equilibrium, if we're in equilibrium, what's our acceleration exactly as a number? Which means forces must be, I'm looking for a word that starts with the letter B. So do you know how big friction is compared to tension? Same size. Okay? So it wants me to find the minimum coefficient of friction. First thing I'm going to make a little note is I'm going to say, okay, although, wait a minute, is there more than one rope in this question? So I'm going to call this tension 1, since it's the first one I wrote. It seems to me we need to find this before we can find the coefficient of friction. So let's walk over here and do a free body diagram where the ropes connect. What are the forces acting on that? Get the obvious one. I have M2G. I guess I have tension 1 going that way. That's the Newton's third forces come in pairs phenomena. And I have tension 2 going this way. Mr. Dueck, how come tension 1 has a equal and opposite pair, but tension 2 doesn't? It does. The wall would be feeling tension 2, but do we care about the forces that the wall is feeling right now? I'm not going to bother. Here, I'm going to do a vector triangle like we've done for a couple of questions. I'm going to draw the easiest vector first. What's the easiest vector? Gravity. Yeah. Is that okay? M2G. I'm going to draw the toughest vector next. Of tension 2 and tension 1, which of those two is uglier? T2. Ready? Tell me when to stop drawing T2 exactly. Why do I have to stop exactly right there? Because I know T1 is dead horizontal. And did I arrive back where I started from? That's a net force of 0, not accelerating. So this is going to be tension 2. This is going to be tension 1. And what's lovely, hey, this is going to be SOHCAHTOA trig. I just need one angle and I'm good. Did they give me an angle in the picture? And I notice when tension 2 is next to a vertical line, it's a 42-degree angle. So this angle is 42 degrees. How big is this angle? Now, I could find tension 2. I don't want to. What do I want to find? Which tension? Tension 1. Why? Because that's also friction. Why? Because then I can find mu. You follow the chain reaction of events here? So, first thing I'm going to say is color, 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 color. M2G, opposite, adjacent, or hypotenuse. What about tension 1? Which trig function? Tan. So I can say tan of 48 equals m2g over tension 1. Noah, what do I want to get by itself in this equation? Where is the tension 1 right now? On the, you know what? Tension 1 is m2g divided by tan 48. Stuff moves diagonally. Right, Lee? I would multiply T1 to the top and I would divide the tan 48 over. I could crunch that, but you know what? I'm just going to walk it right over here. I'm going to say, okay, friction apparently equals m2g over tan 48. However, Noah, friction is also what times what? I don't know the normal force. Oh, but look. Another force the same size as the normal force. M1g in this case. So I'm going to get this. Mu M1g equals M2g all over tan 48. Something kind of weird happens. What cancels? No, the masses don't. But what appears in everything? Turns out this will be in equilibrium on any planet. Doesn't mean it will only stay still on Earth. If you beamed this to the moon, that coefficient of friction would still be enough to hold everything in place. If you beamed this to Mars, same idea. That's why I wanted to do this one algebraically, just to show you, hey, cool. And in fact, how would I get the mu by itself, Noah? Divide what? You're saying dividing the mu to the bottom would get the mu by itself? I want to get the, it said find the minimum coefficient of friction. That's, hey, what's mu? I don't know what's mu with you. Yeah, divide M1. So final answer, mu is going to be M2 all over M1 tan 48. Noah, I've scrolled down. What was M2? M2? What was M1? 12 point. Thank you. Is that correct, folks? Yeah. Mr. Dueck, doesn't that 5.25 have to be bigger than 12.3 to keep everything in place? No. It just has to have enough friction to keep everything in place. I have no idea what the mu is. Hopefully it's not bigger than 1. I tried to make up good numbers. What'd you get? 0.384. Anybody else? Yeah, so actually that's pretty slippery. This is actually going to hold it in place pretty well. Units, Noah? Is it a force? What? No, this is one of the only things that we had, because think about it, it's newtons divided by newtons to get the mu by itself. Even the newtons would cancel. Apparently, when I used to cover this, I used to get to this right around Christmas time, because this is the Christmas card for smart people. I'm sure I stuck this into the lesson. Okay. In the diagram below, assume the mountain climber's feet are tending to slip down, so friction is up. It says, write force equations relating the force components. Find the chord tension, find the normal force from the wall, find the force of friction between the climber's shoes and the wall. Okay. Well, what are the forces in this question? Get the obvious one. There is a tension. What else? Yeah, I think there's a normal force from the wall. What else? Which way is friction going to be pointing? friction is pointing up. What we're going to do with friction, because we're treating this climber as a dot, let's pretend friction is just pointing up right there. Okay? So what we have is this. I'm going to re-sketch this a little bit, but what we have is gravity down. Draw that. We have a normal force pushing out. We have friction pushing up. And we have tension. You know what my best strategy for solving this one when I have three nice forces and only one force that's at an angle? At an angle? This one lends itself to components. I'm going to break tension up into tension X and tension Y. And I guess this angle right here is 8 degrees, right from the picture. Now, why is that nice? Well, I get a couple of equations here then. I think what I get is the normal force equals tension X, everything right equals everything left, or everything left equals everything right. It's those two. And what about vertically? Everything up is going to equal everything. So everything up, tension Y plus friction has to equal mg. So A says write force equations relating the force components. I'm just going to put a part A next to this line because that's what I just did. Okay. B wants me to find the chord tension. That's going to take some effort. Let's see. Let's see. Well, let's start with here, maybe, I think. And I want to find tension. Do I know M? Do I know G? They told me that, yes? 650 newtons. Mg is 650. So I know this. I'd like to see if I can get only two variables in this equation. Right now I have tension and friction. Wait a minute. Friction is what times what? Okay, so I would say this. 650 equals mu times the normal force plus tension Y. You okay with that? Why is that nice? I don't know the normal force. Oh, but look. What's the normal force the same size as? Okay, I can now say 650 equals mu tension X plus tension Y. Why is that so nice? Because now the only force that I have that I don't know is tension. Now it's tension X and tension Y, but let's see if we can bring in the trig and bring in the components. So if I look at this diagram here, there's my right angle, color. Tension X, opposite, adjacent, or hypotenuse? Opposite. Which trig function is opposite over hypotenuse? Which trig function is the opposite one? Tension X is going to be, unfortunately, you can't go Y is sine. That worked great for ramps because the ramps were always going to be in the same orientation. These diagrams are too complicated. But if you notice what we have over here is opposite and hypotenuse, I would say this. The sine of 8 degrees equals tension X over that. Okay with that, Julian? Which means if I get the tension X by itself, tension X is tension sine 28. Sorry, sine 8, not 28, Mr. Dueck. Sine 8. And I can stick that down here. I can say 650 equals mu, what's tension X? t sine 8. What about tension y? Any guesses which trig function tension y is going to be? Of course you can guess which trig function. Yeah, notice it's adjacent over hypotenuse. I would walk over here. I would do exactly the same thing, Brandon. I would get tension y equals t cos 8. T cos 8. Ava, what's B asking me to find? How many t's do I have? How many would I prefer? You know, it would be really cool if there was a Math 9 operation that I could pull out of my back pocket and change which one. I can factor it out. Excuse me. Get the t by itself. Lean, how would I move the bracket over? Yep. Tension is going to be 650 divided by mu sine 8 plus cos 8. And I think they gave me a coefficient of friction, did they not? Yeah, 0.65 right from the diagram. So I'm going to go to my calculator right now. It's going to be 650 divided by mu 0.65 sine 8 plus cos 8. And I forgot the s of cosine when I wrote co 8. Cos 8 degrees. I have no idea what the answer is. $601.44. By the way, if you have grippier shoes, mu gets bigger. If this number on the bottom gets bigger, what happens to tension? Yeah, if you've got grippier shoes, the rope doesn't need to pull as hard. So the fact that that works, I think I've got this set up correctly. Oh, what if you have no friction? This would be zero, huge tension. Okay, that works for me. Quick look of money. We're not done yet. C says find the normal force from the wall. Well, now I'm good to go because now I can say the normal force equals tension X. And if I get tension X by itself, oh, I already did, haha, right here. It's going to be the tension that I just found times the sine of 8 degrees. So it's going to be answer button, sine of 8. 83.7. And D, find the force of friction. Oh, friction is mu times the normal force. Mu was 0.65, and the normal force is sitting in my answer button, isn't it? Force of friction pointing up, I get 54.4 newtons. Now, this question here is actually very tough. I walked through it because I wanted to give you an application of where we can use this stuff. But what I'm going to give you in the homework is from the ultimate review. I'll tell you which ones you can do. You can try number 2. Now, number 2, they gave you both tensions and they're asking you to figure out mg. I would use the sine law here. You can try number 6. Yeah. Try 12. I'd like to find one where the angles aren't the same. Ah, here we go. 15. That'll probably... Ah, there we go. 22. That's the one I was looking for. Okay. 22 is a bit tricky. They didn't give you the angles up at the top, but they gave you all three angles. Add vertical lines and horizontal lines and see if you can figure out what needs to go where. If you can't, is that going to be trickier than I think, Mr. Dueck? Let me think here. That's 100 degrees. Okay, that's 140. That's 120. How would I find the two angles in the triangle? Oh, that'll actually make the triangle way easier to draw, I think. See if you can figure it out. I'll pause here.